Hi, Damien. Thank you for joining in.
Hello.
Hi, Damien. Can you hear me okay?
Yes.
Oh, great. Thank you for joining in. Let me go ahead and share my screen. So if you don't mind, we'll give just a minute or two to see if anyone else shows up, and then we'll go ahead and get started. All right, thank you for waiting. We'll go ahead and get started. Just as a reminder, in the announcements, I have been posting the videos from our class meetings. So the video from our last class meeting on the last Tuesday is available. And if you hadn't taken a look out there, also notice that, there are quite a few videos, extra videos, in addition to the ones from our class meetings that I've made available to you. Don't forget there's extra resources that I sometimes use to work example problems. And just, any number of reminders for the class to help you stay on track. So, some of them, as you can see, are delayed to post at a later time, but all of them are designed to keep you on point and keep you, on schedule with the various assignments and activities that you have to complete for the course. So I'm going to go ahead and jump into the weekly overviews. And you can see here that for this week, we actually have two topics that we have to focus on. That is momentum and work and energy. So I'm going to go into the momentum overview first, and then afterwards, we'll stop for a moment to answer any questions that you might be having, and then jump right into the work and energy overview. All right, so as you can see from the objectives, we're going to be focusing on things like what is momentum. We'll look at its counterpart, impulse. And we'll see some examples of calculating momentum and impulse. In fact, I'll be using the extra notes to look at some examples of calculations involving momentum and impulse. We'll have our first introduction to a concept called conservation as it pertains to, in this overview, momentum, and then you'll see in the next overview, we'll use that concept to deal with energy, work and energy. We'll look at collisions because collisions are the type of motion that we primarily use momentum to help us with. And then we'll look at the relationship and connection between momentum and impulse through the momentum impulse theorem. Bear with me just for a second, if you don't mind. I'm gonna move because I have some company here right now and they're being a little loud. So I'm gonna, if you don't mind, I'm just gonna step into a different room where I can shut the door actually. So bear with me for a moment.
Okay.
That's the beauty of teaching from home, right? Okay. So bear with me. All right. So yeah, I think it's a little bit quieter here now. So, all right. So just to take a look at the activities that go along with this overview. So you have a discussion that's due by Saturday. Problem set 8 is due Saturday. Now remember, problem set 8 actually deals with gravitation that we covered last week. Your second bonus is due, and I'll look at that in just a moment. There's a simulator visualizing collisions that you can try out. It's nothing, there's no assignment attached to it. It's just to have a visual way of looking at collisions. So you might want to try that, as part of your getting comfortable and familiar with momentum and collisions. And of course, to help you with this material, there's chapter 7 in your textbook. There's a series of videos that can help you. There's the simulator that I made mention of, and then the notes that I'll be covering here shortly. Okay, so before I jump in, I want to go ahead and take a look at your second bonus and make sure that you understand what's involved, and then you can ask me any questions you might be having about it. Okay, so this second bonus is dealing with Newton's laws, and I call it my Newton jet car challenge. So this bonus is what I like to call flexible, because it's worth 10 points, but you can add it to several of the assignment types that you've come in contact with. You could add it to problem sets. You could add it to discussions. You could add it to the midterm. You can't add it to the project. You could add it to the final exam even if you wanted to. You can't add it to the project or the overall course score. Those are the exceptions, okay? So if you decide to do this bonus, you will have to let me know where you want those extra points added, okay? Now, so you have to use the materials in the listing below to construct a car, and you want it to be able to travel as at least 3 meters or as far as possible. And the listing of materials include scissors, which are for cutting, and then the other various items are for building the actual car. So tape, 4 plastic lids, those are like drink cup lids, or I've even seen some folk use like soda bottle tops for the wheels. It just depends. If you're not sure about any of the materials, you can always reach out to me to find out what if what you're thinking about is acceptable. Skewers, those are like what you use for shish kebab that you put like on the grill. My suggestion is to use wood or plastic, not metal. Straws, a balloon, and then a tray. A tray can be like an aluminum tray, aluminum foil tray, or a styrofoam tray, a cardboard tray. In any of those types of trays will work just fine. So what you have to do is to build a car, and of course, I have to see evidence that you built the car. And I guess I should add that to the listing here. I sometimes I take it for granted. So you must also include a picture or video of your car, right? Because how else will I know that you built it if you don't send me some type of picture or video, right? So again, use these materials. You build a car, you want it to go as far as possible. You do a write-up that explains how each of Newton's laws applies to the motion of the car. I don't tell you how long. I just tell you that that's what has to be part of the write-up, and a picture or video of your car, okay? So you submit those 2 things, the write-up and a picture or video of your car, and it's worth 10 bonus points, and you can add those bonus points to whatever assignment category you choose, except the project or your overall course grade. Okay. So if you have any questions, feel free to just unmute and ask.
No, I don't have any questions. When is the the bonus due?
Okay, so according to this thing here, your second bonus, let me go back. Okay, I think it should say this Saturday. But I'm not, I'll be honest with you, if you needed a day or two or a little bit more time to get it done, that's fine too. I've been trying to be flexible with things like that. Mostly I try to explain to students that the deadlines that I give are designed to help you not to fall behind. But if you needed a little extra time and you wanted to get it done, no problem.
Okay.
All right. Okay, so that takes care of that. Those are the assignments that you have on your plate for Saturday. And again, these are the resources that you have available. So I'm gonna jump into the information on momentum, and then I'll go into the announcements and look at some examples of solving problems dealing with momentum. Okay, there we go. All right. So momentum. Now you see it referred to here as linear momentum. We'll just refer to it as momentum because we don't really deal with angular momentum in this class. So, we're only going to focus on one kind of momentum. So technically we call it linear momentum, but since it's the only kind we'll deal with, we can just say momentum. All right. So the way you find momentum is you multiply an object's mass times its velocity. So we use the symbol P to represent linear momentum, or momentum in our case. And the way you find it is you take an object's mass and multiply it times its velocity. Now you have to remember that velocity is a vector, so momentum is a vector. And it means that things like direction are important. Objects that have different directions have different momentum. Even if their mass is the same, even if their speed is the same, if they're pointing in different directions, the momentum is different, okay? So mass times velocity, that's fairly straightforward in terms of finding an object's momentum, okay? There is a connection between a momentum and Newton's second law. So when we look at how an object's momentum changes with time, we're actually finding the net force. So if we say delta P, which is change in momentum, divided by delta T, which is change in time, that's another way of finding the net force. And if you recall, net force is equal to mass times acceleration. That's Newton's second law. So in utilizing the change in momentum, we have an alternate way of expressing Newton's second law, okay? So now the question becomes, what are the units involved in this new property, momentum? Well, momentum is found by taking mass times velocity. So mass has unit kilograms, velocity has unit meters per second, so we multiply them together, kilogram meters per second. Be careful, because a lot of times students make mistakes and saying this is force. Momentum is not force. Momentum is kilogram meters per second. Force is kilogram meters per second squared, right? Although the change in momentum is related to force, be careful, because momentum by itself is not force, okay? So a property that's very closely related to momentum is called impulse, okay? And the way they got that was just multiplying both sides by delta T. So you can see change in momentum is equal to net force times change in time. you can see clearly that all they did was they multiplied this side on the left, F net times delta T. And when you multiply the right side by delta T, the delta T cancels out. So you have another way of looking at the change in momentum, and we call that impulse, okay? So it explains here that the impulse is equal to the net force times the change in time. So you apply a force for a certain time interval, and that produces what we call an impulse, okay? So if you look at that equation that's in the box for impulse, it shows what is behind the equation. What the equation really means is that you can get an impulse by having a large force act briefly, or a small force acting over a larger period of time, okay? Either will produce a large impulse or a large change in momentum. This talks about the idea of the average effective force. We don't really need to get into that. What it's really trying to give you an idea of is that typically when we look at this impulse equation, we're that F net we're typically looking at as the effective force. But for our problem solving, the force times the time interval, the force times delta T is what produces an impulse. So you don't have to worry about that too much, okay? Conservation of momentum. So this is a term that you see all throughout physics and all throughout science, to be honest, this idea of conservation. And when we say conservation in this sense, we're not talking about like save the whales kind of conservation, although I agree that that's very important. It's not what we mean here. In this particular scenario, what we're talking about is a property being kept constant, okay? So when we say that momentum is conserved, it means that it remains constant over time if our system is isolated. So an isolated system, imagine we could put a group of objects in a bubble, and we can keep out all outside forces, meaning the net force is 0. That means within that closed isolated system, momentum is going to be conserved for those objects, okay? And so what we do is we express the conservation of momentum in terms of the total momentum, because if we have a group of objects, what we have to do is look at how much momentum each object in our group has, then add it up. And no matter when we do that for our system, we'll always get the same total, okay? So for our isolated system of objects, now remember, we've gone from looking at one moving object to a group of moving objects. That's one of the reasons why momentum is valuable, because we can analyze the motion of a group of objects instead of just one single object, okay? And the key is, for that group of objects, we have to keep them isolated, meaning no outside forces can interact with those objects that are in our closed or isolated system. And if we can do that for that group of objects, the total momentum is constant. And that's what you see expressed in the equation. The total momentum is constant, okay? So it means that anytime we look at our system for that group of objects, the total momentum is always the same, okay? Now you may be thinking, when is that useful? Well, when we deal with collisions, okay? The conservation of momentum is a very useful property when we analyze collisions. Now they give you an example of collision, these subatomic particles being involved in a collision where momentum is concerned. We won't be analyzing this type of subatomic motion because we don't deal in the microscopic world in here. What we're interested in looking at is macroscopic objects. When I say macroscopic, I mean large objects, right? So, things that our eyes can see, for example, that's what we focus on. Cars, planets, things like that, right? We look at the the momentum being conserved, okay? So what are some types of collisions? If momentum conservation is valuable to help us analyze collisions, and we don't need anything fancy to understand what a collision is. A collision is just some objects bumping into each other. So we have a group of objects bumping into each other, and for that closed off or isolated group, the momentum is conserved, okay? So the first type of collisions that we want to look at are called elastic collisions, okay? For an elastic collision, the kinetic energy, which we'll learn about here shortly, the kinetic energy is conserved and the momentum is conserved, okay? So the objects for an elastic collision, the momentum is conserved, the kinetic energy is conserved, and the objects bounce off of each other when they collide. So imagine a pool table where you're playing a game of pool, you know, 8-ball in the corner pocket type pool. When the balls hit each other, they bounce off of each other. That's an example of an elastic collision. In that isolated system of the balls on the pool table, momentum is conserved, kinetic energy is conserved, and the objects bounce off of each other. They don't stick together, is what we mean, okay? So we'll see what we mean by kinetic energy in just a moment, but just imagine for now, whatever it is, momentum is conserved, kinetic energy is conserved, and the objects rebound, okay? So here's a picture of what we mean by an elastic collision, okay? So you see here, we have these two objects in the top of the picture, M1 and M2. And you can see that they're both moving to the right with each one has their own velocity, V1 and V2. So now if we take M1 times V1, we get the momentum for object 1. If we take M2 times V2, we get the momentum for object 2. We add them together and we get a total, P1 plus P2. That's the total momentum. And notice, you see that little, it looks like a oval shape that's surrounding them. Why? Because remember, our system has to be isolated. No outside forces can get in. That's why our system is frictionless, right? Okay. So no extra forces going on there. All right. Now let's look at that same system at the bottom picture. Same two objects, M1 and M2. But notice they're now pointing in opposite directions. You can see the green arrows. They're pointing in opposite directions. That is because they hit each other and then rebounded off of each other in the opposite direction. Okay. So now what we have to do is we add up the momentum again. So we take M1 times V1 prime. That's what that means afterwards. We get the momentum one after. Let's take M2 times V2 prime. We get its momentum after. When we add it up, we still get the same total. So no matter if we look at the system at the before the collision or after the collision, the momentum is the same, meaning the momentum is conserved, okay? What about inelastic collisions? Your mic is open. If you could ask them to kind of, or just mute your mic so I can't hear the background. All right. So inelastic collisions, meaning they aren't going to bounce off of each other. They're going to stick together after the collision, okay? So for an inelastic collision, the momentum is still going to be conserved, but the kinetic energy is not going to be conserved, okay? Whatever kinetic energy is that we'll figure out here in a moment, it's not conserved, meaning the total is not always the same, okay? Momentum, the total is always going to be the same, but kinetic energy, the total is not going to be the same and it's not going to be conserved, okay? The other identifying factor for an inelastic collision is that the objects stick together. And so we focus on perfectly inelastic collisions because after our objects are stuck together. Okay. So here's a visual. Your mic is still open. Let me stop the share for a moment. Okay, let me mute you. Okay. So I apologize for that, but I had to mute you because the background noise was kind of interfering. All right. So here you can see a visual of an inelastic collision. Okay. And you can see that in this particular collision, which our system is isolated before the collision, no external forces, still frictionless. You can see that their velocities are such that they're pointing toward each other. So we know if they keep moving toward each other, eventually they're going to collide. Okay. And so if we look at the momentum of each object before the collision and add it up, we get a total of 0. Well, they're the same mass, but their velocities are opposite. So when we multiply mass times velocity and add those together, we're going to get 0. So if the total momentum before they hit is 0, the total momentum after has to also be 0. Okay. So the difference is that if you notice the objects after the collision, they're stuck together. All right. So if they're stuck together, we treat them as a combination. So no longer are they two separate objects, but they're one larger object with a mass of m plus m in this case, right? We have to add their masses together. And they move with the same common velocity afterwards, okay? So before the collision, they're both moving, they hit each other, stick together, and they move together. In this case, they stick together and they stop. But in some instances, you will see that the objects will stick together and move together, okay? So for an inelastic collision, the momentum is conserved, kinetic energy is not conserved, because you can see here in the picture, the kinetic energy before the collision was mv squared. The kinetic energy after the collision is 0 because they're not moving, okay? So, momentum is conserved, kinetic energy is not conserved, and the objects stick together. All right, so that's what distinguishes our elastic from inelastic. I see somebody with on iPhone chatting me saying the computer screen went black. I'm not really sure. I'm sharing. Can you see it now? Can you type and tell me if you're seeing it now?
Hey, this Damien. I had to log back on my phone. I'm loading my computer back up. The screen went black, so I couldn't see anything.
Okay. Well, so you're right now. I see Damien logged in, and I see iPhone. So it's the same. That's the same one person, right?
Yeah, I'm trying to log back in on my computer.
Okay, no problem. Just if something goes wrong, you'll always have access to the video.
Yeah, I emailed you when it happened. I don't know if you got the email.
No, because while I'm chatting, while I'm sharing, I can't see any of that.
Okay, I'm sorry.
No problem.
Okay.
All right. All right. So again, remember the whole idea behind momentum is that we want to use that to help us analyze collisions. Now, these last few slides talk about the rocket problem, rocket propulsion. We're not going to get into that. That's beyond anything that we cover in this class. Sometimes you hear people say, it's not rocket science. Well, indeed, when you're studying momentum and, collisions and reactionary type systems, it is in fact rocket science, because that's exactly the kind of motion that momentum conservation is exactly the kind of motion where you study propulsion and rocket motion. So it truly is rocket science, but we won't get into that, okay? So what I want to do now is I want to go under the announcements, and I want to bring up our extra notes, okay? Extra resources, right? So if you click on the link, it will open a folder, and you will have access to momentum notes. Now, the nice thing about this is that there are some really nice problems worked in these packets. This screenshot basically is like a summary. There we go. I wanted to zoom in. Okay, so let me zoom in just a little bit more. So you see, I talk about in this summary kind of slide for the conservation of momentum, where momentum is not changing. And that is useful because we want to talk about momentum being conserved or staying the same before and after a collision. And then we look at the types of collisions: elastic, inelastic, and I break down the definition and difference between the two of them. More importantly, for the inelastic collision, I give you the equation that you use to solve problems for an inelastic collision. We don't solve problems dealing with elastic collisions because that math is above what we do in this class, but you can surely solve problems dealing with an inelastic collision, and we'll see a couple of examples that relate to momentum conservation. Okay. So I like this packet because it breaks down definition of momentum again. Even nicer, it shows you how to use the problem-solving pyramid to solve momentum problems dealing with the momentum equation. And it shows you the units involved for each one. So momentum, another definition for momentum is the quantity of motion. Objects with a high momentum have more motion. And so you can see, we know to find momentum is mass times velocity. And then when you multiply the units, kilogram meters per second, that's how you get the units for momentum. All right. So here's an example. Find the momentum of a bumper car if it has a total mass of 280 kilograms and a velocity of 3.2 meters per second. Okay. So gave us mass, gave us velocity. Our pyramid says if we want to find momentum P, we multiply mass times velocity. So that's 280 kilograms times 3.2 meters per second, 896 kilogram meters per second. Okay. So for that particular bumper car, that's the amount of motion that it has, 896 kilogram meters per second. Here's another example of using the momentum formula. The momentum of a second bumper car is 675 kilogram meters per second. What is its velocity if its total mass is 300 kilograms? So this time they gave us the momentum and the mass. And if we want to find the velocity, remember with the pyramid, whatever you're looking for, that's what you cover up, and then you multiply or divide. So in this case, we're looking for velocity. So we have to divide momentum by mass. So that becomes 675 kilogram meters per second divided by 300 kilograms. That gives us a velocity of 2.25 meters per second. Because remember, you have kilograms meters per second in the top, and you have kilograms on the bottom in your denominator in this case, so the kilograms will cancel out. Okay. So that's the example of using the momentum formula. Fairly straightforward, right? Multiply or divide to find the variable that's missing. The law of conservation of momentum, remember the whole idea here is what? The total momentum before equals the total momentum after. And again, the different types of collisions. So for an elastic collision, momentum is conserved, kinetic energy is conserved, the objects bounce off of each other. For an inelastic collision, momentum is still conserved, kinetic energy is not conserved, and the objects stick together, okay? So now, remember, we don't solve problems dealing with an elastic collision, but we can surely solve problems dealing with an inelastic collision where the objects are stuck together afterwards, all right? So let's take a look at these next few examples. It says a 5 kilogram cart traveling at 4.2 meters per second strikes a stationary 2 kilogram cart and they connect. Find their speed after the collision, okay? So now we have these two carts, okay? That's our system. No outside forces, momentum is conserved, meaning the total momentum before they hit is equal to the total momentum after they hit. So let's figure out the momentum for each object, add it together to get our total before. So the first cart has a mass of 5 kilograms and is moving at 4.2 meters per second. So we multiply that, 21 kilogram meters per second. Well, what about the second cart? Well, it has a mass of 2 kilograms, but they told us this was stationary, so its velocity is 0. So it doesn't have any momentum. If the velocity is 0, it's not moving, the momentum is 0 because V is 0. All right, so what's our total? 21 kilogram meters per second. How about after the collision? So after the collision, remember, they're stuck together because it says they connect. So we have to treat them as one object, right? So the way we get that cart 1 plus 2 is to add their masses together, which is 5 plus 2, 7 kilograms. And the whole idea is for this combined system, what is their velocity? What, you know, if they're stuck together, they both have to move with the same velocity, okay? So let's figure it out. The only way we can figure this out is if we use our conservation of momentum, which tells us that the total momentum before 21 kilogram meters per second has to be the total momentum after 21 kilogram meters per second. So now what do we know? We know the momentum, we know the mass. So if we want to get the velocity, we take the momentum divided by the mass. 21 kilogram meters per second divided by 7 kilograms gives us 3 meters per second. Okay, so see how we use the conservation of momentum to help us find the velocity afterwards. Speed, but speed plus direction, right? We know that these carts are moving together in the same direction. So it's not like, you know, we're ignoring that there is a direction involved, okay? Let's take a look at a second example. And this one is a little bit more involved, a little bit more of a thinking question. This kind of problem that you see here in this example is important because it's the kind of a problem that you will see on your problem set number 9, okay? Problem set number 9 deals with momentum. And this is a common type of problem that you'll see on that problem set. So it says here, a 50 kilogram clown is shot out of a 250 kilogram cannon at a speed of 20 meters per second. What is the recoil speed of the cannon? Okay, so now you envision this clown inside this cannon, somebody fires up the cannon, the cannon fires, the clown goes flying, and the cannon recoils. That's what they want to know. How fast does the cannon recoil? We know that recoil, another word for that is kickback. So how much does the cannon kick back when it fires, okay? So we go to our conservation of momentum, okay? Because this is kind of like a collision in reverse, if you will. They're together before the collision and separated after, but it's still an inelastic collision from the perspective of momentum conservation, okay? So let's see how much momentum before. Well, clown isn't moving, cannon isn't moving. So the total momentum before is 0. So that means that the total momentum after also has to be 0. Okay. But let's look at the momentum of each, the clown and the cannon after. Well, the clown goes flying. They said what? 20 meters per second, right? Well, the mass of the clown is still 50 kilograms. Speed is 20 meters per second. Momentum is 1,000 kilogram meters per second because we multiply those two. What about the cannon? Well, they told us the mass of the cannon is 250 kilograms. And that's what we're trying to figure out. How fast does it recoil? Well, see, now we've got to do a little bit of thinking, because if the total momentum after has to be 0 and the clown has positive 1,000 kilogram meters per second, what's the only thing I can add to that to get 0? Negative 1,000 kilogram meters per second. So positive 1,000 plus negative 1,000 gives me 0. But see, the only way I can get that negative 1,000 is to know that the total has to be 0. And I know that the total has to be 0 because the total before was 0. And momentum conservation says whatever the total is before has to be what the total is after. Okay. So now that we know, oh, sorry, let me go back into it. My bad. Now that we know the momentum of the cannon after, and we know the mass of the cannon after, we can find out how much recoil was involved. So negative 1,000 kilogram meters per second divided by 250 kilograms gives me negative 4 meters per second. And remember, this is a vector. Velocity is a vector. The negative sign tells me that the cannon recoils backwards. Positive means forward, so negative has to be backwards. Okay? So those are some examples of utilizing the momentum formula and the momentum conservation formula. Okay? Well, what about its counterpart, impulse? How do we use that to help us? Well, just as a reminder, here's another definition of momentum. Momentum is a measure on how difficult it is to stop a moving object. Well, that makes sense, because if momentum is a measure of how much motion an object has, an object with more motion is going to be more difficult to stop, right? And we know that momentum is a vector. Okay, so direction matters. Direction matters. Okay, so you could think of the idea that objects with a high momentum can have a big mass, a velocity, or both. So you could have a charging elephant with a large mass, maybe not as big a velocity, but the momentum is going to be high, and so it's going to be difficult to stop a charging elephant, right? Or you could have an object with a small mass and a high velocity, a bullet, small mass, very high velocity, very large momentum, very difficult to stop, right? All right. So we've seen this formula, F times the change in time equals the change in momentum. That's impulse, right? So that's our impulse momentum relationship, right? Change in momentum equals impulse, okay? So as we said, to produce an impulse, a change in momentum, you could have a large force over a short time period, or you could have a small force over a larger time period. Either way, you're going to produce an impulse. So that's what's happening, for example, when you swing a golf club. When you swing a golf club, you want to have good follow through. And that means that you're going to keep the club head in touch with the ball throughout the swing, producing a larger time interval, producing a larger impulse, meaning the ball can travel further. Same thing with batting, for example. Okay, good. A person that is a good batter, like a home run hitter, for example, like the guy who just hit 60 something home runs, Judge, I think is his name. So the idea is that when he hits the ball, he has a very good follow through in his swing. So the baseball stays in touch with the bat throughout his entire swing, meaning not a large force and a large time interval producing a large impulse. Well, what's important about a large impulse? Well, when you produce a large impulse, you have a larger change in velocity. A larger change in velocity means the ball can go further because you're going to make it, you know, you're going to have a higher acceleration, produce a bigger distance. Okay. So that relationship that you see here in this last equation is called the impulse momentum theorem. It relates impulse, force times change in time, to change in momentum, the difference between the starting momentum and the final momentum. Okay. So here's an example problem utilizing the momentum impulse theorem. It says a 1,400 kilogram car moving westward with a velocity of 15 meters per second collides with a pole and is brought to rest in 0.30 seconds. What is the magnitude of the force exerted on the car during the collision? Now, one thing you need to pay attention here, 0.3 seconds is a very short time span. That's what makes collisions so deadly. They happen in an extremely short period of time, okay? And so let's see what force is generated here. So we start with our impulse momentum theorem equation. Let's fill in the things we know. Well, we know the time interval, 0.30 seconds. We know the mass. We know the final velocity. We do because it says it's brought to rest. So the final velocity has to be 0. The minus sign comes from the formula. The mass that we start off with is still 1,400 kilograms. And then the initial velocity. This is very important here because they said 15 meters per second west. Remember, vector language, west means negative. So we have to put our negative sign there to indicate direction, and west is negative. All right, east is positive, west is negative. Okay, so now let's solve this. Well, 1,400 times 0, that's 0. Negative 1,400 times negative 1,500, negative 1,400 times negative 15, excuse me on that, gives us positive 21,000 kilogram meters per second. So now what we need to do to get F alone, divide both sides by 0.3, and we get 7 times 10 to the 4, or 70,000 newtons to the east. How do I know it's to the east? Because it's positive. All right. So this car runs head on into this pole, comes to a stop in 0.3 seconds. That's less than half a second, and generates 70,000 newtons of force in the process. Okay. The question then becomes, well, if this collision generates that much force, you know, what in the world can we do to make these collisions less deadly or make them generate less force? Well, we can see very clearly from the equation. One of the things we can do is, if we want less force, we have to make the time last longer. So the question becomes, what can you possibly do to make a collision last longer? Airbags. That's the function of an airbag in your vehicle. The airbag is designed to allow you more time to come to a stop so that there isn't as much force involved in the collision. Okay? So if we increase the collision time to a half a second. So we go from 0.3 to 0.5. So now divide 21,000 by 0.5, you get 42,000 newtons. So we went from 70,000 newtons for 0.3 seconds to 42,000 newtons at a half a second. So we increased the time by 0.2 of a second and dropped the force by almost half. So that's what an airbag does. okay? So the combination of a seatbelt and an airbag, the seatbelt protects you from Newton's first law, the airbag protects you from impulse. All right. The other thing that's really, really nice as a visual, and in fact, it's in the weekly overviews for momentum, so I'll just go right there. And that is the visualizing collision simulator. So you might want to try that out. And it's really nice because you can see the collisions happening, right? So we can just take a simple collision. We want to see momentum. We want to see change in momentum. We want to see kinetic energy. We want it to be totally elastic with a constant size. You know, you can vary those things if you want to and play around with it. And okay, pause it. The other nice thing is if I click that more data, it tells me about the the velocity, and I know the masses of each one of the objects, right? I know the velocity of each one, and I know the momentum. Let's see. Yeah, the change in momentum is also showing here. Let me see, maybe I need to see where that screen is at. I'm looking for it on the screen. I don't see it. Maybe I have to hover over the objects. Let's see. Okay, yeah. Okay, so, oh, so basically what you can find, you can get the change in momentum here by looking at the before and after for each one of them, right? So if you know the mass of each one, and I cut, oh, let's see if it doesn't show the values right off the top. Yeah, I was looking for a screen that showed me, you know, oh, there we go. There you go, total, okay? So you can, there, I didn't have it open there, okay? So you can see the total value, and then let's just reset it, and restart it. And what you can reset, oh, refresh, duh, okay? And we'll click all those values again, my bad. We'll make it keep it an unconstant size. We'll look at more data. And watch this little total value down here at the bottom, the little black arrow. Let me see if I zoomed in, okay? So now let's watch the total. You see? So we made it 100% elastic, and the value, the total momentum stays the same for these two, okay? All right, so you see the momentum before 0.7 kilogram meters per second, 0.5 kilogram meters per second, and they're just giving the size. That absolute value is just giving you the size. You know they're pointing in opposite directions, all right? They're giving you the absolute value or the speed in this case. And then you basically, you figure out then before this one has positive 0.5, before this one has negative 0.75, because it really points in the opposite direction, right? And then if you look at it, you know, then you look at the situation after the collision, they literally almost, you see, they go back in opposite directions. I let it go too fast, but okay, let me do it in slow motion. Let me restart it. But you get the idea here. You can play around with this. You can vary things to show you different values. I won't even put kinetic energy on there just to keep it simple for right now. And you start it. Okay. And so so you can see the values, you know, after the collision for each object. And you can see the values before the collision for each object. Okay. So, and then you can make them inelastic as well. I'll reset it, make it totally inelastic. And then you'll see in this particular case, okay. Oh, maybe let's see. I thought I made it inelastic there. Okay. There, you see, there is inelastic, how they stick together afterwards. Okay. So it's just a cool little simulator to play around with, to kind of have a visual on what happens during collisions. Okay. And you can play around with it. There's also another very good one. Actually, I like this one a little bit better, to be honest with you. If you go under simulators and you choose the one that says elastic, inelastic collisions. Okay, and this one I'll do in slow motion. And I like this one because you can very clearly see that if I started, the total momentum before is 0.1, the total momentum after is 0.1. I'm dealing with an elastic collision. And that means the objects have to bounce off of each other, okay? I'll reset it, I'll make the collision inelastic, same idea. The total momentum is the same before and after, but in this particular case, the objects stick together, okay? So I like this one better because it's a little bit easier to visualize. If I put it on kinetic energy, you can see the kinetic energy for an inelastic collision is not the same because the total before is this and the total after is that. What about if I make them elastic? Okay. Now I see that the total energy, kinetic energy, excuse me, is conserved, right? So I like this one a little bit better because it's a little bit, you don't have as many bells and whistles to manage, okay? All right. So again, you can use the visualizing collisions, or you can go in the simulators link and click on the one that says elastic and inelastic collisions. All right. So before I move on to working energy, we can just take a few minutes and see if there are any questions that you might be having at this point. Okay, I'm not sure if that means you're still having some technical difficulties, but
yeah, my computer is blinking off and on. I don't know if it's the computer or is the your screen. I don't know.
No, mine is actually quite stable. Yeah, I don't see anything happening off and on where mine is concerned.
It's black. It went pitch black.
Yeah, I think that's probably happening on your side. Okay. Yeah. So let me just, you may not be able to see it, but let me just kind of talk you through where you can get information to help you with this topic. Okay. So if you're with the working energy topic, okay, so you may not be able to see what I'm doing right now, but if you go under announcements, okay, and I'm going to post a video from this class, but also there are extra videos for just a time like this. So you see, there's extra videos for Newton's laws, gravitation, momentum, working energy, and thermodynamics. There's extra videos for all of those topics right there in the announcements. It says extra videos, and one of the topic areas is momentum and working energy. There's an extra video for every topic that we cover. So there's extra notes, there's the videos from our class meetings, and there's extra videos for every topic. So for some reason, this doesn't work out good for you, the video that I'm making now, then you can always go and watch the one that's there. It's pretty much the same thing that I'm covering. Okay. So I hope that will help you out. All right. All right. So now I'm going to go into the work and energy overview. And so in this time, and I can hear the mic open in the background.
I can't close it. My computer went black.
Okay, let me see. I can do it. All right. Okay. So now, hopefully you can still hear me. But in this particular overview, we focus on work and energy. So we're going to look at the different types of energy. We'll look at what is work and what's the connection between work and energy. And then we'll look at conservation of energy. Okay. So for this overview, problem set 9 is due Saturday. Now, problem set 9 deals with momentum. Okay. So this week you got 8 and 9 on your plate in terms of problem sets, and you have the energy discussion. And then the second bonus if you want to do it. Okay. To help you, there are 2 chapters in the textbook, chapters 2 and 8. There's a series of videos dealing with energy, and then my supplemental notes dealing with work and energy. Okay. So in this one, I'm going to cover my notes, and then I'm going to point you in a direction of a resource that can help you not only with visualizing energy and energy conservation, but also some kinds of applications where energy conservation is concerned. All right. Okay. So, so one of the things we want to do is we want to contrast work and energy in physics versus everyday life, right? Because in everyday language, we use the words work and energy all the time. We use them in casual conversation. You know, where do you work? Okay. Buy me an energy drink. So we use those words in casual conversation, and the everyday usage is in some roundabout way connected to our physics definition, but we have to be careful not to equate our everyday casual conversation to the way we define them when we deal with them in physics. Okay. So the beauty is that over the course of our developing our understanding of energy, we've figured out that there are a lot of different types of energy, different forms of energy, and the good thing is that they're interchangeable. Okay, and that's pretty important because it's been a guiding principle in a lot of the things we've been able to achieve in terms of using our environment to our benefit. Okay, so first let's talk about work. Okay, so when we talk about work, we don't mean like what we say every day, where do you work? But what we mean in physics is that there's a transfer of energy involved. So there's a force that's causing an object to move, and in the process, energy is being transferred. Okay, we use the letter W, capital W, to denote work. Please do not mix up this W with the W for weight. Okay. The way we calculate work is we multiply force times distance, force times displacement. Okay. And the key is that the force and the displacement have to be in the same direction. So if you exert a force on an object, you have to cause it to move in the same direction as the force you're applying in order to do work, in order to produce an exchange of energy. All right. So to calculate work, W, we multiply force times displacement. Okay. And they have to be in the same direction. The units, here's a new property, work, that we can measure. So every property has its own unit. So in this case, to get work, we multiply newtons for force times meters for displacement, and we get the unit joules. Joules is the unit of work in the metric system. And the way you find it is to multiply newtons times meters. Okay. There's a relationship between work and energy called the work energy theorem. And if we want to know the amount of work done, the net work done, we look at how an object or system changes its kinetic energy. Now, we hadn't formally defined kinetic energy, but here you see it being used. 1/2 mv squared, kinetic energy, 1/2 times mass times velocity squared, okay? And if we look at the difference between the starting kinetic energy and the final kinetic energy, that tells us how much work is being done. That's called the work energy theorem. Gravitational potential energy, that's another type of energy, right? Kinetic energy, 1/2 mv squared. Gravitational potential energy, mgh, okay? So whenever we do work against gravity, an object stores up energy. Another way to say that is when we lift an object to a certain height, that object stores up energy based on its height, okay? That stored energy based on height is called gravitational potential energy, okay? The way we find that is mass times gravity times height. Now they say delta, typically we start from zero height on the ground. So the starting potential energy is 0. So in that case, we just talk about mgh, okay? So as an object rises and falls, we can store up and release potential energy, all right? As you lift an object to a certain height, it stores up gravitational potential energy. And when you release it and it falls, it releases that potential energy, okay? And so what they're trying to show you here in this visual is that as you store up energy, the amount of energy stored is equal to the work being done. So you're storing up energy, mgh, and you're doing work, mgh, okay? When you let go of the object and the energy is released, you can use that energy to do work, okay? Conservative forces. So any force that can produce work that does not depend on the path taken is what we call a conservative force. So in other words, the amount of work done only depends on from where you start and where you stop, not how you get there. Any force that does work and only depends on where you start and where you stop in terms of the motion. Because remember, to do work, you have to move an object, right? You have to move the object in the direction of the force. So when you do that, and you only have to figure out where you started and where you stopped, it doesn't matter how you get in between, what you do in between those points, we call that a conservative force. Gravity is an example of a conservative force, okay? All right, so when you're dealing with work done, as it pertains to gravity, then you're dealing with a conservative force, and it doesn't matter how you get from one height to another. It only matters what was your height when you started and what was your height when you stopped, okay? And so in that situation, we know that when we're dealing with a conservative force, mechanical energy, mechanical means motion. So energy associated with motion is going to be conserved. Well, what types of energies are associated with motion? Kinetic energy and potential energy. So when you're dealing with a conservative force, mechanical energy is conserved. So if that means what? The total amount of kinetic and potential energy that you start with is going to be the same amount of kinetic and potential energy that you finish with. The total of the two is always going to be constant, okay? So if you look at the kinetic energy at the start, the potential energy at the start, you add them up, that is going to be the exact same amount that you're going to have when you add the kinetic energy final plus the potential energy final. Okay. There are non-conservative forces. And these forces, remember, conservative forces don't depend on the path, but non-conservative forces depend on the path. Friction is an example of a non-conservative force. So it matters how you get from start to finish, okay? So you still compute the work done by force times distance, but in this case, the path or the distance or displacement covered matters, okay? How about work done by non-conservative forces? So if we're going to maintain this idea of work, of using the law of conservation of energy, but we want to include our non-conservative forces done, we have to come up with a way to determine that non-conservative work because we can't measure it directly. We can't measure the work done by friction directly. So we measure it by looking at those energies that are modified because of it, okay? So we add up the kinetic energy that we start with, the potential energy that we start with, plus the work done by our non-conservative force like friction. And then we look at the total kinetic energy and potential energy afterwards, okay? So that allows us to figure out the work done by the non-conservative force. And that becomes the change in kinetic energy plus the change in potential energy. If we look at how our kinetic energy changes and add it to our potential energy change, that will tell us how much work is being done by our non-conservative friction force, okay? So we can write the law of conservation of energy in a broad sense for all types of energy by looking at the kinetic energy, the potential energy, work done by a non-conservative force, other types of energy. We look at them at the start, and then we look at them at the finish, and those totals must be the same, right? Another way of saying that is we cannot create or destroy energy, but it can change form. Okay, energy cannot be created or destroyed. It can only change forms, okay? And what are some other forms of energy? Chemical, electrical, nuclear, thermal, radiant, all of those different types are various or other forms of energy. And when we look at the totals in our systems, then for it to be conserved, then the total must always stay the same. Efficiency, while we don't necessarily do problems with this, it is a good idea to understand that efficiency means, how much work out are we getting for the energy that we put in? We're putting energy into a system, how much work are we getting out, okay? Now, the thing about efficiency is that we typically express it as a percentage, and our workout is never going to equal to our work in, so it's always going to be less than 100%, okay? So efficiency means how effectively are you using the energy that you're putting in? How much work are you getting out? Well, we can see here that there's a chart here of some various efficiencies, okay? And you can see that there are some processes or activities that are very, very inefficient, right? Look at swimming, for example, 2% efficient. Well, you could think of it this way. When you're swimming, any heat that you're generating is automatically being zapped by the water that you're in, right? So it's very inefficient. You aren't getting much work out for the energy that you're putting in. But look at, for example, an electric motor, 98% efficient. That might explain why we're trying to move to electric vehicles, right? Because compared to gasoline engines and diesel engines and steam engines, you can see that the electric motor is much, much more efficient, okay? Power. Power is the rate at which work is done, okay? So work per unit time. The unit for power is the watts. So that's a new property, power, work per unit time. So for our power, the unit is the watts, as in your 100-watt light bulbs, for example. And 1 watt is equal to 1 joule per second. Okay, so a 100-watt light bulb is 100 joules every second. A 100-watt light bulb is using 100 joules of energy, or you could think of it this way: our 100-watt light bulb is doing 100 joules of work every second. Okay, and then there's a relationship between the English system and the metric system. 1 horsepower, which is the English system, right? You know, like you hear Hemi engine, for example, horsepowers or horses. So 1 horsepower is 746 watts. And then this just talks about the idea of energy conversion in humans, this metabolic rate, and it looks at various organs in terms of, you know, the metabolic rate at you know, how efficiently or effectively it converts food into energy that the person can utilize in bodily functions, right? So you see here, in terms of organs that use up a lot of the energy, the food intake, right? The liver, for example, you see is like very, very energy intensive. Well, you know, the liver is a key organ in the digestion, and, you know, and the kidneys, for example, you see they're not as involved in digestion, but they don't show an organ on here as the pancreas, which, you know, is very much key in terms of producing insulin that the body uses. Well, the liver is a big part of utilizing that insulin effectively, and also in terms of storing fat and those types of things in the body, right? And look at the brain. You know, you would think that, okay, the brain is one of the major organs and it's controlling everything that's going on in the body, so it must be very energy intensive, but it's not. And the heart is even less, right? So pretty interesting to look at, you know, how the organs in the human body convert energy. And then these last few slides are just informational, and they talk about, you know, projected energy consumption. You know, we're facing some of the consequences of that now these days, especially at the pump, so to speak. And you can see the projected energy use is just, you know, projected to go up and up and up, right? And then power consumption, well, you see, you know, per capita, you can see the more developed countries are utilizing more power. But, you know, as some countries are becoming more industrialized, that definitely is changing. Okay. But it's no magic that we're near the top, right? All right. So that's energy. What I wanted to do was to go in the announcements. I'll go right in here. And I'll bring up the extra notes folder, and there's a folder on energy. Okay. And the nice thing is in this packet is they define each one of them for you. Okay. Kinetic energy. All right. Potential, gravitational potential energy. Work. Okay. And then there are a few simple examples utilizing the work formula. Okay. Where you multiply force times distance to get the work done. And then I like this particular example because it highlights the fact that that you have to be, your force and displacement have to be in the same direction, or there's no work being done. The classic example is given here of where you have a force and a distance, but no work is being done. And that is in the case of carrying an object. When you carry an object, as in this example where they're lifting the ballerina and doing work, but then once they lift the ballerina, they're walking around with the ballerina held up, right? So they're carrying the ballerina, And so in that instance, there's no work being done because the force and the distance are perpendicular. If the force and the distance are perpendicular, that means they're not in the same direction. And they're carrying an object, so no work is done. Okay. Also, I like this example because they don't directly give you the force involved. You have to calculate the force involved by taking the ballerina's mass, in this case 40 kilograms, and multiplying by G, gravity, to get the force involved, the ballerina's weight. So do not mix up weight, which is a force, in this case 392 newtons, with work, which is force times distance, which is 549 joules of work being done to lift the ballerina. And then after the lift, walking around with the ballerina, no work is being done because the force and distance are perpendicular, not in the same direction. Okay. And then the rest of this talks about conservation of energy, gives some visuals. I'm going to take you out to a site to show you some actual animations here in a moment. And then they finish up by talking about power, the rate at which work is done, and the unit of power. Okay, so let me take you out to under useful links. We'll go back to our simulators. Okay, back to our simulators. And this time we're going to bring up here, we're going to go back to something we've seen before, our projectile motion. Okay. And in the past, when we focused on projectile motion, we didn't focus on force and energy, but this time we're going to. Okay. So our projectile, if you notice, has a total energy of 61.6 joules that is starting off with, and watch, all throughout the motion of our projectile, the total energy remains at 61.6 joules. And the question may be, how is that possible? Because I see the kinetic energy and the potential energy changing, right? Well, remember, gravity is a conservative force and the projectile operates under control of gravity, okay? So because the projectile operates under the control of gravity, mechanical energy, kinetic and potential are conserved. Another example of a system where the energy is conserved, okay? So let's take a look at the energy. So we see kinetic and potential energy here, all right? So now let's watch. You see, the energy is alternating between kinetic and potential, but the total energy is always staying fixed in this case at 0.747 joules, okay? So now you see at some point during the swing, it's all potential. And then as the pendulum swings, the energy goes all kinetic, all potential, all kinetic, back and forth. When the pendulum is at its high points, it's all potential. When the pendulum is straight up vertical, it's all kinetic, but the total is always the same. Well, why is that the case? Because this pendulum is being controlled by gravity. And gravity is our example, primary example of a conservative force. Our primary example of a non-conservative force is friction, but a conservative force is gravity, okay? And then you can look at a spring pendulum as well. You can see the spring is the same thing, because if we look at the energy involved with our spring, we see that it also oscillates between kinetic and potential, but the total energy is fixed, because this is an example of a conservative system that's being controlled by a conservative force, in this case, gravity, okay? And then one of my favorites, if you go to the physics classroom under useful links. So the simulators, there are simulators that show the energy conversion. the physics classroom is a tutorial site. And if you go under there and you go to work, energy, and power, notice this site has a coverage of every topic that we cover. So you can go there. The nice thing is that there are some practice problems that you can try. And then I like it because there's a visuals of the idea of mechanical energy being conserved, and roller coaster. That's a simple roller coaster where you have mechanical energy being conserved. But here's a nice one here. I can't do the animation. At least I don't think I can. Yeah, I can't do the animation on this one. So we'll just stick to the visual here. The idea is that at any point along the motion, the total amount of energy is what we start with, which is 40,000 joules. The total at the start, which is here, is 40,000 joules. What about when we get to the bottom? Well, you see, we were all potential, but now we're all kinetic. But the total is still 40,000 joules. What about at the top of this first loop? Well, we split between the two, but the total is still 40,000 joules. What about here, this smaller loop? 2515, but still 40,000 joules, right? No matter where we're at along the motion, no matter where we're at, the total is always 40,000 joules, because this roller coaster, it is gravity driven, is no friction, which we know that that's not how things work in the real world, right? But because there's no friction involved and only gravity, mechanical energy is going to be conserved. Okay, so that's a nice visual. And in fact, I would suggest to you that you come out to this website and try some of the examples that they have, sample problems, to get familiar with the idea of conservation of energy. It's not only useful for this lecture class, but it's very useful for what you're going to be seeing in the lab class. Okay. All right. So that's pretty much what I wanted to share with you tonight. I'll stop the share and ask if there are any other questions. I know you're having some difficulty seeing the screen at all, but here's what I suggest, Damien. Just email me any questions that you might have, and I'll be happy to address them for you. This recording is going to be available in the announcements. Give me a couple of days to get this out there. So since you're having screen difficulty, you definitely want to go back and take a look at it. Okay. So I do appreciate you hanging in there with me tonight. And, you know, take a look at the recording and email me any questions that you might have. Okay. So that's about what I have for you tonight. Have a great rest of your evening. Thank you for hanging in there, Damien.